Once again, good morning to all of you, and let us begin with the session for the day. This is your course instructor, Khushwant Fatnani. Will begin with a prayer. I request all of you to please join your hands, close your eyes, one by one, 3 deep breaths. Take a deep breath in and a deep breath out. Once again, breathe in and breathe out. Breathe in once more and breathe out. Now, let us pray. Kindly repeat after me. Dear God, I thank you for this life and all the blessings of life. I thank you for such good health, wealth, and wisdom. I am grateful for all the support of my family members, friends, and colleagues. Dear God, I thank you for the dream you have placed in my heart. Thank you for all the knowledge, skills, wisdom, and strength you have given me to fulfill that dream. I know and I believe that I have already cleared NEET 2020, JEE Advanced 2020 in flying colors, NEET 2021 in flying colors, and I have got admission into the college of my dreams, one of the best IITs in the country, one of the best aims in the country. I know and I believe that I've already achieved this dream with your grace. Thank you in advance. Thank you, thank you, thank you. Now, I request you to kindly, very slowly and with a smile on the face, to open your eyes. All right, let's start. Let's begin. All right. So today we are going to see oscillation and waves. So one recheck, in case you're able to clearly hear me, class, please raise your hand. Okay. In case you're able to hear me, class, please raise your hand. So we have with us Aditi, Atul, Karuna, Anukriti, and Mahila. So good morning, all of you. Once again, let us start with all the energy. And I hope you all are doing very fine. Let's start. So before I begin, I want any one of you to give your understanding of what all you can recall in this chapter. Yes. So let us take Atul. What all are the terms, or let's say type of numericals or topics that you can recall from this chapter? Everyone can bring their hands down. Thank you. I would like Atul to tell us what all do you remember, right, from this chapter. Although I'll be telling, but then yeah. Yes, Atul, get going.
What all terms, sir?
Yeah, anything you can recall from this chapter, terms, type of problems, etc. Yes. It can be anything. Don't worry. Yeah, yeah, go ahead. Go ahead. Yes.
Like in this chapter, we will study about like wavelength frequency
Wavelength,
and
frequency, right? Excellent. Excellent.
mm,
Okay, keep going. Don't worry.
time period, etc.
Time period. Absolutely correct. Time period. Yes, there's topics like time period, wavelength, frequency. Yes, yes.
Wave equation,
Wave equation. Wave equation. Right, right.
um, um,
Yes, yes. That's excellent. Now, thank you, Atul. Let us take Anukriti. Yes, Anukriti. So, would like you to recall and try recollecting whatever knowledge you have in mind, whatever terms you can recollect as you think of this unit, oscillations and waves. Yes, even it can be as simple a term as simple harmonic motion, right? Yes, go ahead.
So that's what I was about to say. SHM and Doppler effect
Doppler effect. Yes,
and
absolutely correct.
and oscillation. That's
Excellent.
all I can recall, sir.
Yes, yes, yes. You all are doing very good, right? Even like randomly somebody asks you and you recall all of these terms, it's a good achievement. It's a good thing. Yes. Excellent. Let's take Karuna. Yes, Karuna.
Okay.
So it was first discovered when a pendulum was oscillating, and when the pendulum uh, does a one rotate.
Right. So there is one simple thing that we have learned apart from the terms that you also just told. Karuna is giving an example of a pendulum. So in laboratories, we conduct an experiment where we try to find out what is the G value or acceleration due to gravity value by measuring different time period values. Excellent. Excellent. That is a kind of oscillation. Very good. Very good. What else? What else? That's excellent. Yes. Excellent, Karuna. What else does try recalling from the chapter oscillation and waves? So let us now. Anything else, Karuna, you would like to say? Yeah.
So beats.
Beats, right? Doppler effect, beats. Okay, okay, excellent. Yes, so these are terms from the chapter waves, right? Right. Excellent, Karuna. Excellent. So excellent. Mahila, would you like to add something else? Anything that comes to your mind when you read about this term, oscillation and waves?
Sir, we will be learning about periodic and acceleratory motions in our oscillation chapter, sir.
There is something called as periodic motion. There is something called as accelerated motion. Okay. Anything else? Any word that comes to your mind, strikes your mind when you think about it?
We'll be learning about forced oscillation, sir,
Forced oscillations.
and its resonance.
Resonance, forced oscillations. Very good. Excellent. Excellent, Mahela. So, class, let us begin. I think I have taken views from all of you, right? Yeah, so Aditi is also there. Aditi, anything you would like to add?
Energy in simple harmonic motion.
Energy of simple harmonic motion. Very good. Very good. Excellent.
Damn simple harmonic motion.
Damped and forced simple harmonic motion. Very good. Excellent. ठीक है. Great. So thank you everyone. Let us start off with the session. So in this session, in this chapter, oscillation and waves, there are pretty good number of points that we'll cover, right? So I'll write some of them over here, right? I hope you all will be able to connect with it. So what we are going to see will be something in this order, right? Something in this order. So although there is a lot to see in this chapter, right? But we'll see a quick summary of everything and everything which is required, needed to recollect the chapter and its essence. So let us have that quick revision. So we'll be studying about the main topics in the chapter, like periodic motion, as Mahila said, as Atul said, right? Periodic motion. Class, note it down, right? Then we'll be having an insight of what is a simple harmonic motion, as Anukriti reminded us. Then we'll be seeing the different aspects of a simple harmonic motion. So we'll write this as force and energy. Force and energy in SHM, right? Then fourth one is we'll be seeing some examples like simple pendulum, as Karuna reminded us, right? Simple pendulum. Next, we'll be seeing topics like oscillations of a spring. How does a spring work? We'll also see free, damped, and forced and resonant vibrations, right? So free, damped, forced, and resonant vibrations. So all this is a part of the chapter, mostly oscillations, right? So since we are covering the unit together, oscillation and waves, right? So after this, we'll start the chapter waves, which has different topics like, so this is from the chapter SHM or oscillation, while another topics from the chapter waves will be want you all to note this down with you, right? Topics like what is a wave motion, what is, then we'll be reading about the speed of different waves, right? We'll be reading about the speed aspect of a wave, right? We'll talk about sound waves, right? We'll be seeing the displacement relation the displacement relation. So for a harmonic wave or a progressive wave, mark the word, it's a harmonic wave. Okay, harmonic wave. All right, all right. Something very close to an SHM. We'll think about it. We'll see that. Then we have concept of principle of superposition of waves. Principle of superposition of waves. We'll talk about intensity and power of a wave. Right? We'll see how a wave is reflected and transmitted. So more importantly, reflection of waves, right? From a denser and rarer medium. From denser and rarer media. Right? Media is plural form. Then we have concepts like standing or stationary waves. Now this includes topics like a string, right? Or a pipe, a closed pipe, an open pipe, right? Stationary waves. Then we see concepts of beats and Doppler's effect. So class, once you have finished noting these topics, raise your hand. Yes, class. So class, please raise your hand once you are finished writing the topic. Yes. Okay, great, great. I think everyone is done writing, so we'll begin. Now talking about different oscillations, what is a periodic motion, etc., and beginning with the concept, right? So class, this chapter or this unit, oscillation and waves, invites first of all the distribution. Let us see, like every time, what is the distribution of this chapter. So class, from this chapter, like the concept of oscillation and waves, if I count, nearly every year at least 2 to 3 questions are asked from this unit, right? Asked from this unit, especially the topics like beats, right? Doppler effect, right? Then the topics like stationary waves. These are never ever left. In every year's paper, you'll find 1 or 2 questions popping up from these units, right? These super important units, right? And you always get questions from here and there. So in 2003, we had, I think, around from this chapter, so I can see that in 2003, there were nearly 8 questions that were asked from this unit. And I suppose that in those days, only one paper used to happen. So this amount is a very big thing, right? Is a very big thing. Similarly, in 2002 also, I can see huge number of questions were asked. So around 7 questions were asked in the year 2002. Yes, Karuna, tell me, you want to ask something? Yes. Okay. So class, this is the kind of distribution, right? Every year in the syllabus, and talking about NEET, right? Talking about NEET. So around 2 to 3 questions every year from each chapter, oscillation and waves. So let's say we are talking about the year 2009. So I can clearly 2009, where when PMT was held, right? CBSE PMT. So 2009, I think, saw around 4 to 5 questions coming up from this unit, right? 4 to 5 questions coming up from this unit. So this is how things are arranged, class. Around 4 to 5 questions were asked in the year 2009 in CBSE PMT. So you can take an average of around 5 to maybe a 5, let's say 5 to 6 questions coming up in NEET exam also from these two units, right? So we'll make sure class that we are very much thorough with the revision. Whatever revision we do, that is a thorough revision, so that we can very easily attempt questions. Let's start off, right? First of all, we'll see the term whenever oscillation or vibration is taught to you. What do we mean by oscillation or vibration? Very simple. See here, I'll draw, let's say, a straight line, right? Now I am saying that there is a particle which is moving along the straight line, a particle which is moving along the straight line from one point to another. Let's say here is the particle, right? So this particle is moving on this straight line from one point to another. Now, what do we mean by periodic motion? First thing, so any motion which is repeating itself, any motion which is repeating itself after a given period of time is called a periodic motion, correct? So I represent a periodic motion as y of t, that is, displacement is a function in time such that after every t time, so let's say I call the period of the function as capital T. So after every t time, displacement value becomes same. It means that if the time period is 6, if the time period is 6 and at t is equal to 0, particle was found here. If at t is equal to 0, the particle was found at the center of some motion, then again after t is equal to 6, it will be found here. Again after t is equal to 12, it will be found here, right? So again at t is equal to 18, it will be found at this same location, right? So it is saying that the displacement of the particle becomes same after every given time interval, which is known as time period, right? Which is known as time period. This is what a periodic function is. Now, when I talk about this term as simple harmonic motion, of course, motion means something is moving, right? Motion means something is moving. Simple implies something is moving with a fixed amplitude. Class, I'll repeat. Simple implies something is moving with a fixed amplitude. Harmonic means it's a function in sine and cos. It's a function in sine and cos. It's called harmonic. All right. So we will have let's say this particle. So this particle with a fixed amplitude is undergoing a sine and cos vibration, sine or cos based vibration in a manner such that whenever it gets displaced from its position, so let's say the particle was at the center, right? It got displaced and came to a new position, let's say over here. Okay, so the particle was initially at t is equal to 0, it was here. After some time it came to a new position and its displacement from its initial position is equal to x, right? And x is towards the right side, it's towards the right side. So according to the concept of simple harmonic motion, when a particle is displaced in the right by x direction, then a force starts acting on it in the left direction, given as with magnitude of k into x, with a magnitude of k into x. So since its direction is opposite, I call this force as F is equal to minus kx. Any particle in the world which is being acted upon by such kind of a force, F is equal to minus kx, such a particle is said to be in simple harmonic motion. Such a particle is said to be in simple harmonic motion. Right? Now, class, we can write this as F. We know F is equal to ma. Which chapter? Recall the chapter of Newton's laws of motion had taught us that the second law gives us this expression, F is equal to ma, and this is nothing but minus kx. We have learned, class, that A is equal to dv by dt, right? We have also learned that A is equal to v dv by dx. We have also learned that v is equal to dx by dt, right? Try recalling. I hope and I'm sure that you will be able to. As we write this term, let us try converting this expression in that term, m times of a. Instead of a, we can write dv by dt is equal to minus kx. Instead of v, we can write dx by dt. Right? This gives us m times of d2x by dt square is equal to minus kx. Correct? Now I can write this as m times of d2x by dt square plus k into x is equal to 0. Class, this is also, on an obvious note, equation of a simple harmonic motion. See how we transited from one kind of equation to another, right? Now class, what I do, I divide both sides by m. See, I divide both sides by m in this equation. What do I get? See, I get d2x by dt square is equal to minus k by m into x, correct? Now, let us say I will call omega square as k by m. So this equation becomes d2x by dt square is equal to minus omega square x, right? What is d2x by dt square? d2x by dt square is acceleration. So I have acceleration is equal to minus omega square x, right? And acceleration is minus omega square x, and I have f is equal to minus kx. F is equal to minus kx. These are the two expressions. I can see and try to understand that, okay, whenever I see these expressions, I will understand that the particle is undergoing a simple harmonic motion. So as Mahila has rightly said that, sir, we'll read about accelerated motion. So in any simple harmonic motion class, what is happening? What is happening is we have a path, right? We have a path. On this path, there is a particle. There is a particle. This particle, this particle keeps on moving in a fashion that, so let's say if the particle was initially at this point, I call this point as x is equal to 0. See what I've written here. Class, have a look. I've written that the particle is in the state of, like on it a force is acting minus kx and it has fixed amplitude. See here, it has fixed amplitude, right? So it has fixed amplitude. So what is happening is, after some time, the particle reaches over here. After some time, the particle reaches over here. This position is x is equal to a, right? And here there is a position x is equal to minus a. So what happens? Particle goes from the center, reaches this new position, right? Comes back from there. So let us draw this. So it goes to this new position, right? Comes back from there to the center. Then from the center, it again goes back, right? And again comes back to the center. So this is called as one oscillation. This is called as one oscillation. And what is happening all this while? As the particle is on the right, as it has got displaced positively by a distance x, a force is acting on that particle in the backward direction. See here, a force is acting on the particle in the backward direction with the magnitude kx, and its direction is in the opposite direction of x. So if the displacement is towards right, force will act towards left, right? So what this is doing, class, try recalling, we have done this in the class, that whenever particle, so in this position actually particle is moving forward, but the force is acting in the backward direction. So whenever velocity is in the forward direction and force or acceleration is in the backward direction, Karuna, tell me what should happen to the particle. Should its speed increase or should its speed decrease?
Decrease, sir.
Very good. Excellent. So what is happening is, as the particle is going from the center to the end points, these are called as ends or extreme. These are called as ends or extreme. And the center position, so as the particle goes from this point to the extremes, there will be some opposing force acting on it, which will reduce its speed, and ultimately the particle will stop at the extreme positions. The particle will stop at the extreme positions. Then this force which was acting on this particle will try to bring it back to the center, but as soon as its displacement becomes negative, right, after some time, right? So right now displacement is positive only because it's on the right side here. So until here, what will happen? I will just draw the diagrams once again. So this is the straight line, right? We have particle was here at the center, right? Here, one more interesting fact. At the center, since x is 0 and f is equal to kx, we have just learned that f is equal to minus kx. So Atul, how much should be the force at the center?
0.
0. Very good. What happens when the particle reaches the extreme position? What should be the force here when the particle is at x is equal to a? Yes, Atul.
Minus Ka.
Very good. So here the force will become minus Ka. That is, the direction of force is in this direction, right? Now,
Yes.
here as I told, when the particle was transiting to this extreme position, what was going here, its displacement was positive, so the force was acting in the backward direction. Therefore, acceleration was acting in the backward direction. Therefore, here was the velocity, but the acceleration was in the backward direction. Therefore, speed was decreasing, right? The speed was decreasing. That means if the speed at the center, if I take that speed to be maximum at the center, V max, then that speed becomes zero at the extreme positions. Are we clear with this, Atul? Because the speed keeps on decreasing as the particle is moving towards right. At one point, the speed becomes zero at the extreme position. Are we clear with this, Atul?
Yes, sir.
Okay. Then again, the particle comes back to this extreme position over here, right? Over here. And in the similar pattern, as it is moving backwards, the force is acting in the forward direction. See here, class, as the particle is moving in the backward direction, that is, its displacement is negative, its velocity is negative, right? The force is acting in the forward direction because F is minus kx, so it is in the opposite direction of x. So acceleration is in the forward direction. Again, that will be nothing but retardation. Why? Because velocity is in the backward direction, acceleration is in the forward direction. Again, speed decreases. As the particle is going back, again speed decreases, right? So what happens is, again, when the particle reaches here, its velocity becomes zero, right? And what is this point? I call this point as x is equal to minus a. So see here, class, this is fixed value. A is a fixed value, so I call it amplitude, right? Class, are we clear with this? Mahila, can you tell us about the values of velocity, force and displacement at the three positions A, B and C? Yes, Mahila. Can you just repeat what I just said? Yes, go ahead. So you need to tell us that what is the value of velocity, force and displacement at the three positions. Yes, Mahila, get going. This is 1, this is 2, right? And this is 3. Yes, Mahila, tell us. What is the value of displacement, force acting, right, at the three positions? Yeah, and the velocities. Yeah. Okay, no worries, no worries. Karuna, can you tell us? Yes, Karuna.
So x at A is minus A.
Very good.
X at B is 0.
Okay,
X at C is A.
very good.
F at A is minus kx.
F at A is Ka because it's in the forward
K.
direction, right? So
Yeah.
see here, see this expression. If here you will put x is equal to minus A, you will get F is equal to minus K into minus A, which is equal to Ka, correct? Therefore, I've written Ka over here. Is that clear, Karuna?
Yes.
Okay, okay, great. Yeah, yeah.
F at B is 0.
At B, force is 0. Okay, all right.
Uh,
Yes.
at C is minus Ka.
At C, it's minus Ka. Very good, very good. When the displacement is positive, force is negative. Here, when the displacement was negative, force was positive. Very good. Okay, what about velocity? Yes.
Velocity at A is 0.
At A is 0 and at C is also 0 at C.
Yes, sir.
Why? Because it's the extreme position. At the extreme positions, the velocity is always 0. And
At B,
Yes, class.
It's maximum.
Yes, class, this position B is called as mean position. A and C are called as extreme positions. A and C are called as extreme positions. B is called as mean position, and at mean position the velocity is maximum, right? The velocity is maximum. Now class, such kind of a motion, if I want to trace the displacement of the particle, it is a harmonic function. So harmonic means which is a function of sine and cos, which is a function of sine and cos. So x can be given as a sine omega t plus phi. This is the general expression of a simple harmonic motion. General expression for displacement. For displacement of a simple harmonic motion. Note it down, class. This one is a general expression for displacement of a simple harmonic motion. Now trace these things, class. Here x is nothing but displacement of the particle. Displacement from where? From mean position. That is, in our case, point number B. Point number B. So from mean position, displacement from mean position, right? Then we have A is the amplitude. Amplitude implies by how much maximum distance has the particle got displaced. It's called amplitude. X max, right? Then what about omega? Try recalling. We had written omega square. See here, we had written omega square is equal to k by m. Yeah, right? So what is this omega? It's k by m, and it's called as angular frequency. Right, this class? Angular frequency. Why is it called as angular frequency? Because it is a product of 2 pi and f. 2 pi and f, where what is f? F is frequency. F is frequency. Frequency is how many oscillations per second are being made, or per unit time are being made by the particle, right? So what is f? F is frequency. F is frequency, and you can call it number of oscillations made by the particle per unit time. Per unit time is called as frequency. Then just few time ago you all had said this term. Try recalling, sir. Time period. What is time period? Time period, and time period is the amount of time after which a periodic motion repeats itself. After which a periodic motion repeats itself, right? Repeats itself. And this time period is nothing but 1 by f. Write it down, class. This time period is equal to 1 by f. Therefore, you can also write omega is also given as 2 pi by t. See here, we had omega as 2 pi f, and f is equal to 1 by t. So it can also be given as 2 pi by t. Write it down, class. These are some key points, some hints, right? Of course, we know that t is any given time. T is any given time. What about phi? Now this phi is actually a matter of question for many students. This phi is very simple thing. It's called phase constant. It's called phase constant. It's a constant, and it's called a phase constant. It's called a phase constant. It's also called initial phase. It's also called initial phase. Class, once you have written this page down, please raise your hand. Yes, class. Okay, great. So we learnt about this equation where x is equal to a sine omega t plus phi. Okay. Aditi, I want you to just tell us the definition of each term one by one from this side. Yes, from the RHS. Yes, Aditi, get going.
So which
I think there is some network issue. No worries, Aditi. That's okay. That's okay. Mahila, can you just read the contents from the RHS? Just read it out. No worries. Yes, Mahila. Just tell us what is x, a, omega, t, and phi.
sir X is displaced from the mean position,
Very good. Yeah.
and F is the frequency, which is number of oscillations per unit
Time.
time,
Very good. Very good.
and T is the time period,
Yes. What is omega?
and we have
What is omega?
omega is K upon M, which is angular
Very
frequency.
good. What is A? A is
A is amplitude.
amplitude. Why do we call simple harmonic as harmonic? Why do we call it as harmonic? Because displacement is a function of sine or cos,
Um,
right? Okay. What is phi?
yes, sir. Sir, pi is the phase constant
Or or
or initial phase.
very good. Very good. Now, can you also tell us the formulas that I have written here? The formulas for omega. Yeah. Read it. K by
Omega is equal to K
by.
by M,
What is
sir.
K? What is M? What is K? What is M? Recall we had written F is equal to minus Kx. So this is that K, okay?
Yes,
Right? Okay. Now what about
yes, sir.
M? What about M? M is mass of the body. M is mass of
Mass of
particle, which is oscillator,
mass of the body.
right? We call it as mass of oscillator. Class, write it down. This is mass of oscillator. Are you clear with the terms, Mahila?
Yes, sir.
Pakka?
Yes, sir.
Okay, okay. Now, class, very simple. I am trying to tell you all after this that how do you write down the expression for velocity using this term of displacement. So, how do we get this equation? By the way, this equation x is equal to a sine omega t plus phi comes when you try to satisfy the equation of a simple harmonic motion. That is this particular equation, this particular equation or equation of an SHM is very easily satisfied by the value x is equal to sine omega t plus phi, right? Or the general expression for SHM or simple harmonic motion. So once we have read this class, uh, let us try to draw how a simple harmonic motion displacement graph would look like. See here, class. This is how a sine function looks like. So we are trying to draw how does a graph, let me take instead of x, I'll take it as y this time, and I'll take y is equal to a sine omega t plus phi, right? Class, it's very important to understand this one aspect. See here, This is called phase. This is called phase. This is called phase. So everything that comes after sine or cos, everything that comes after sine or cos, it's called phase. It is nothing but an angle. It is nothing but an angle in which is variable in terms of time, right? So class, this is called as phase. It is very important to understand what phase is. This term omega t plus phi is called as phase, whereas phi is called as initial phase. Why? Atul, try substituting t is equal to 0 in this equation. What do you get? Tell me.
At t equals to 0, phase is equal to phi.
Phi. Yes, absolutely correct. And since we are seeing t is equal to 0, it's called initial phase. It's called initial phase. Are we
Initial
clear now,
phase.
Atul, that why do we call
Yes,
phi
sir.
as initial phase? Because this is the value of phase at t is equal to 0.
At t
Right?
equals to 0.
Excellent.
Yes, sir.
Now we have this expression for sine omega t plus phi represented in this pattern. Right? So we all have seen the sine and cos terms. This is how we represent displacement varying with time. So tell me one thing, Anukriti, what should be the maximum displacement of this function? What should be the minimum displacement of this function? In the top and in the bottom. Yes. Here, y value should
The
be
maximum
a.
should be
Right.
A
What about
and
here?
minus A.
Minus a. Very good. So the particle can be seen oscillating between a and minus a from this diagram, right? It's oscillating, it goes here, comes back, again goes back, again comes back to the original position. So the particle is basically undergoing simple harmonic motion between the points x is equal to a and x is equal to minus a. So we can see that here in this graph. This is the graph between displacement and time, right? This is the graph between displacement and time. Displacement and time, and we can see that how is displacement varying with time. Okay, so great, Anukriti. So class, we have two cases in simple harmonic motion. Two cases. One, if the particle begins its oscillation from the center, if the particle begins its oscillation from the center, right, at t is equal to 0, particle is over here. This is one case, right? Another case is particle is at extreme position. So this was mean position or the central position, x is equal to 0. So if particle is at x is equal to 0 at the time t is equal to 0, and there is another case when the particle is at x is equal to a. So this was x is equal to a, this was x is equal to minus a. This is x is equal to 0. So if the particle starts its oscillation from x is equal to a, then this is second case, and then there is a general case. So if the particle starts its position from any arbitrary position on this line, right? It can be any given position. Say this was x is equal to 0, right? Again, this was x is equal to minus a. This is x is equal to a, right? And a particle starts its oscillation from any given position. Any position, right? So in all the three cases, class, we have different expressions for oscillation which are derived from this equation, right? What was the equation? What was the equation? We just wrote, see here, we had the equation x is equal to a sine omega t plus phi. Okay. So Atul, I want you to substitute in this equation x is equal to 0 and t is equal to 0. Tell me what happens. Yes.
So to find whose value?
Just substitute it. Substitute it. Tell me what happens. What x?
Okay. Mm,
Substitute x
then we
equal
will get
to
a sine phi equals to 0.
okay, so basically what is happening is I am saying that at time t is equal to 0, that is initially, particle was positioned at center or mean position where x was 0, right? So I am putting x is equal to 0 and t is equal to 0 in this equation. Yeah. So what does my expression come out as? Sine phi
A sine
is
phi.
equal to 0, correct?
Yes, sir.
Sine phi is 0.
Sine phi equals to 0.
When does sine phi
Yes, sir.
come out to be 0? At phi
At
value of
phi
0,
0.
right? So when phi is 0, sine phi will be 0. Can I substitute it back here? Phi as 0. What will now equation become?
Yes, sir.
Tell me.
X equals to a sine omega t.
Very good. So x is equal to a sine omega t is the equation of the particle which has started its motion from
Center. Mean
center
position.
or mean position. Very good, very good, right? So this is the scenario. Okay, Atul, can you do the same thing for second one and tell me what will be the phi value there? Yes, get going, try it out. So you have this equation x is equal to a sine omega t plus phi. Just substitute x is equal
Yes, sir.
to a and time is equal to 0. Tell me what happens.
Uh, then phi equals to sine inverse 1. So,
Just try seeing
so
again.
phi is 90.
Very good, very good. Class, see what Atul is saying. He's saying that, sir, instead of x, I will substitute a, and instead of t, I will substitute 0. So my answer will come out to be a and a will get cancelled. So I'll have sine phi is equal to 1, which will bring me phi is equal to 90. Phi is equal to 90. So see what my equation will become. My equation will look like x is equal to a sine omega t plus 90 degree can be written as pi by 2 radians, right? So we'll have a sine omega t plus pi by 2, right? Atul,
Yes, sir.
now sine 90 plus theta, sine 90 degree plus theta. This is 90 degree. Sine 90 plus theta is given as cos theta, right?
Cos theta.
Very
Yes,
good.
sir.
So this expression will therefore become x is equal to a cos theta or a cos
A
omega
cos omega
t.
t.
Are we clear with this, Atul?
Yes, sir.
Class, note this down. Class, note this down. Now, let's say at any arbitrary position, particle starts its motion, right? So let us say, for example, the particle starts in the question. It is given that the particle. So class, on this, take your net first question for the day, right? If the particle starts its motion apart in SHM, in SHM, particle starts its motion, particle starts its motion at x is equal to a by 2, x is equal to a by 2, right? And omega value is given as, or its frequency, I will say, is given as, let us say its frequency is given as 2 hertz. Its frequency is given as 2 hertz, right? Now you have to find out expression for, find out, and its amplitude is a, of course, right? You have to find out the expression for velocity, displacement, and acceleration and force. Yeah, its mass is m. M is the mass of the particle. Okay. Yes. Can you try this question? Atul? Or let us take Karuna this time. Okay. Karuna, can you try this question? How will you go about it? Let us first write the general expression. What is the general expression for displacement in SHM? What is the general equation for SHM? Yes, Karuna.
X is equal to A sine omega t plus phi.
Very good. X is equal to A sine omega t plus phi. Now, what do you have to do in this question, Karuna? What is it saying? The particle starts its motion at x is equal to a by 2. That means in order to find out the phi value, what will be our step? What will we do? Tell us. Yes.
Substitute as A by 2 and t as 0.
Very good. Substitute x is a by 2 and t as 0. Everyone will do it, right? Everyone will do it. Yes. So we'll get, tell me, a by 2
Uh,
here, a
equal to
sine 0 plus phi, right? Something like this. Correct? Karuna?
yes, sir.
So a will get cancelled on both sides. I will get half is equal to sine phi, right? So for what
Yes.
value of phi is sine phi 1 by 2?
Sir, 30.
30 degrees, right? Which is equal to pi by 6 radians. Correct, Karuna?
Yes, sir.
Okay. So when I get phi is equal to pi by 6, how can I now write my equation? X is equal to a sine omega
Is pi
t
by 6.
plus pi by 6. Very good. Very good, Karuna. Now, Karuna, do we know the expression for velocity in terms of displacement?
Yes, sir.
What is the expression? Tell us.
D by dt.
Dx by dt. Very good. So we have right now x in front of us as a sine omega t plus pi by 6. Right? How do you apply here? How do you apply this here? Tell me. D is equal to d by dt of a sine omega t plus phi or pi by 6. Let us first do it for general expression and then we'll substitute phi later. Okay. Yeah. So for a general expression class, if x is given as a sine omega t plus phi, how do you write down the expression for velocity of it, of that particle? We are seeing that general expression for velocity, right? So that we can give a general expression. I can give you all a general expression of how velocity, displacement, and phase are varying, right? So yeah, tell me, Karuna, what is happening?
So A with
A,
differentiation of
A is a constant, so it will come out, right?
yes,
Correct. So what will it? What will
yes,
the equation look like? A and d by dt of sine omega t plus phi. Correct.
yes, sir.
So sine omega t plus phi. Now I can take this entire expression as t and apply chain rule. Do you all remember, class? We had done chain rule in the concept of differentiation. Okay, differentiation of sine should be cos.
Cos.
So this will become a cos omega t plus phi, and then whichever term we had assumed to be t, we will differentiate it again. That is d by dt of omega t plus phi. Right, Karuna?
Yes, sir.
So this expression will become, what will be the differential of the term omega t? D by dt of
Omega.
omega t plus d by dt of phi. Tell me one thing, Karuna. Is this phi a constant or a variable?
Variable, sir.
Try thinking again. See, what did we say? What did we call it?
Angular frequency.
See once again. What did we call it?
Uh, phase,
Phase?
phase constant.
Phase constant. Now tell me, is phi a constant or a variable?
Constant.
Phi is a constant. For a given motion, Karuna, for a given motion, phi is a constant. That is, once the motion has started, the phi value will not change. Am I clear? I'll
Yes, sir.
repeat.
Yes, sir.
Once the motion has started, the phi value will not change, right? So phi is a variable or constant?
Constant.
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 Very good. Very good. So phi is a constant. Okay. So we have d phi by dt as 0 right? And here we have cos omega t plus phi, right? Now, what about this expression d by dt of omega t? What will its value become? Omega,
Omega.
right? So we have omega plus 0, right? Coming in this bracket, omega plus 0, right? Because d phi by dt is 0, right? Because phi is a constant, right? So now what does our expression become for the velocity? V is equal to a omega cos omega t, correct?
Yes, sir.
Now when I have this expression, can you tell me what should be the maximum value of V from this expression?
Um,
See here, what is the, how does cos vary? It varies between sine and, it varies between -1 and +1, right? So let's say cos assumes its maximum value of +1. Cos assumes its maximum value of +1. Then what should be the value of V max? Tell me. V max should be equal to A
A omega.
omega. Very good. So where did we have V max? Try recalling. Where was velocity maximum in the entire motion, in the entire span?
Position.
In the
Mean position.
mean position. Very good. So we'll have V is equal to A omega at the mean position. Write it down, class. Write this down. Right? And here velocity was 0. Here also it was 0. Okay. Now one more thing, class. Once I know the velocity, I can find out kinetic energy, right? So Karuna, can you tell me what should be the kinetic energy at the mean and extreme positions if mass is m for the particle? If this particle has a mass m, what should be the kinetic energy at these positions? Here k will be,
Half.
what will be k?
Half.
Okay, general expression is k is half mv square, correct. So what should be the value of k at extreme positions when velocity is 0? K should be
Half.
0, right? K should be 0, correct? What should
Yes,
be
sir.
K here? What should be K here? K should be equal to
0.
0. Very good. Here K should be equal to half
Half
m
A
into
omega square.
a square omega square.
Yeah.
Class, write this down with you. The value of kinetic energy, velocity, etc. What should be the value of acceleration, Karuna? What is the general value of acceleration we read? Try recalling from here. I'll put it in a
VD.
box. Here, have a look. We saw the general expression for force and acceleration both. What is the general expression for acceleration? Yeah, tell us. Minus
Minus
omega square x, right? So with different values of x, I will have different values of acceleration, right, Karuna? Yeah, can you tell us what will be the value of acceleration at the 3 positions? Yes.
extreme points, it will be 0.
Sure.
Yeah.
A is equal to, the general formula is A is equal to minus omega square x. So what should be the value of acceleration at the extreme points?
0.
Sure.
Omega square A.
Minus omega square A at x is equal to
Fine.
A, right? See, put here
Yes,
x is equal to A. You will get minus omega square A, right? What about the other extreme position? The x is equal to minus A. What should be acceleration here?
Omega square A.
Very good. So acceleration is positive at x negative, and as x is positive, acceleration is negative. What about the center position?
A is equal to 0.
Acceleration is 0 at only the center position. How did this come, class? This came from the general formula for acceleration, which we had seen. Class, very important. Whatever we have read today, if you do not revise all of this, everything will vaporize from your mind. Remember this. If you do not revise this, everything is going to vaporize from your mind. So it's very important that you have a closed look at whatever we have read today, right? Whatever we have read today from the expression we derived, that is this expression for velocity. I want you all have a homework, right? You all have a homework. What's the homework? The homework is you all need to derive, you all need to derive the graph. You need to draw the graph between velocity, and time. We saw a graph today between displacement and time. See here, everyone, displacement and time. What kind of graph it was? Between sine omega t, between a sine omega t and t. Right now, you need to draw a graph between cos omega t, that is velocity, the general expression for velocity, cos omega t plus phi. I think we missed that out. So cos omega t plus phi and a omega cos omega t plus phi and time, right? So here V is a omega cos omega t plus phi. So this is the kind of graph that you need to plot as a homework. All right. So this is how things will go about class, right? We'll continue from here in today's evening class. There is a formula for velocity given as V is equal to A times of under root V times of A under root, sorry, omega under root A square minus X square, where X is A sine omega t plus phi, right? So this is the expression for velocity in terms of amplitude. We also read another formula for velocity, amplitude and displacement. We also read the other formula, right? We also now know that acceleration is equal to minus omega square x. So I can also write this as minus a omega square, tell me, sine omega t plus phi, right? So class, I'll send you all some questions, right? And we will continue our expression of learning from here itself, right? We'll talk about oscillation of a spring, etc., along with solving the questions in the evening class, right? So whatever we have read today is a basic introduction to SHM, right? Therefore, I tried to be minimum with the number of questions. We just went ahead with the basic introduction of an SHM, right? Force, energy, right? We saw some different expressions, right? Now, in the evening class, we are going to see the other parts, other topics, and some numerical solving. So I'll send you all an assignment. Try solving it. Wherever there is any query, you may let me know, right? Thank you, everyone. Thanks a lot. Let's meet up today in the evening session, right? Thank you, class. Thank you very much. You all can log off. Thank you very much, class. Thank you. You can take the screenshots if you require, if you need them to complete your notes. No issues, right?
Thank you, sir.
All right. Thank you, class. Thank you very much.